So what we're going to do today is introduce the basics of bonding and talk about the first two types of compounds and the first two types of bonding, and then we're going to move towards some more detail analysis of one type of bonding. AP chemistry really focuses in on covalent bonding, but I need to get through ionic bonding and the general concepts before we do so. So we know from our lab here where you guys built, okay, or at least my spreadsheet built these graphs for you, and we looked at the periodic table was periodic, and we look at the atomic numbers, and we know that there's periodicity because, well, we're starting with an electron and then we're filling electrons in the same energy level while we're adding to a Z number. And so we see a repeating pattern, okay? And the patterns that we get called the periodic trends that change going across and going down are something we've talked about. This is more about understanding why we have the bonding that we have. So if you look carefully in my three-dimensional graph of atomic radii, we can see that the Waldo, the one that doesn't make any sense, is my hydrogen. And we can see going down a group, the radius gets bigger. It's hard to see, but the smallest atoms are top to the right, and we get bigger going across. And so there's a trend there for atomic radium. And of course, those trends we've talked about. Let's talk about the other trends. Let's talk about ionization energy. Okay, ionization energy, we can see that these peaks steadily go down because the what? The N number gets bigger, harder to remove electrons. But more importantly, yes, there's a repeating pattern, but with ionization energy, if you look at the three-dimensional structure of this graph here, we can see that maybe hydrogen is our what? Our Waldo. It doesn't fit. What do we have? There's tremendous amount of energy it takes to pull electrons, or that energy to pull electrons increases as we go across. There's something about these atoms up to the right that have the greatest what? Ionization energy, which means they have the greatest stability for electrons, or those electrons feel the nucleus more. And of course, we know going across an energy level or a period, the Z number, the protons increases. But we'd expect low ionization energy starting here and increasing. Why? Because these atoms over here are the largest atoms, meaning they have the least number of protons in their energy level. And as you add protons, it takes more what? Steadily more energy to do that. So if you go across period 2, okay, and we have lithium, beryllium, boron, okay, carbon, you can see that the ionization energy is steadily increasing. Why? Because again, the Z number is increasing. Of course, there's going to be some ones that buck the trend because of electron-electron repulsions. But general things to understand is that ionization is larger up to the right, lower to the left. And that's important when we look at the types of bonding that occur. Let's go on to electronegativity. Our graph for electronegativity also has some repeating patterns. Notice that we steadily increase as we go through an energy level, and then it crashes down at the end. If you look at the three-dimensional graph, really cool that the Excel can do this in real time for us, we can see that electronegativity looks a lot like ionization energy, which means the atoms that had the greatest attraction for electrons also take the greatest amount of energy to remove. And notice the Waldo. Hydrogen doesn't fit here. We'd expect small electronegativities. Now, if I didn't already explain, electronegativity is a word that helps us really combine three values: the effect of Z, the proton number, the effect of ZEF, and the effect of N. And certainly we use electronegativity to see how well the nucleus can attract the outermost electron. But more importantly, it's really measured. We only can measure electronegativity in bonded atoms. So electronegativity for the noble gases doesn't really exist because they don't make bonds. Now, there's some that do, so these disappear here. So electronegativity is really attraction of the nucleus for electrons in a bond. And we can only measure that when they're in bonds. So therefore, the noble gases, which we would expect to have the highest attractions for electrons, they have the highest ionization energy, don't have them because we can't measure the attraction for electrons in a bond. They don't make a bond. Notice what? Hydrogen has a high attraction for electrons in a bond, and so do the ones up to the right but low to the left. So let's go to the periodic table to see if we can understand these trends and start understanding the two different types of elements we really have. Okay, so what do the trends really tell us here? The trends are telling us, okay, that the larger atoms are to the left and down. And this makes sense. In this region of the periodic table, there's a fewest number of protons for the energy level, and it's the first, beginning of a new energy shell. So the atoms get bigger going down and to the left. So what do we know about atoms in this region? Well, we know there's some bigger atoms, and it's important we realize what's going on here. So let's talk about what's happening in this region here. Okay, so I'm really talking about the trend as we move down a group, we get bigger as we move to the left. So the the properties I'm talking about are really, really materializing in this area here. So as you go down and to the left, there's something happening. And what's happening is the atomic radius is increasing. Atoms get bigger going down, they get bigger going across. Okay, now from the graphs, we showed that ionization energy, that's the energy it takes to remove an electron, decreases. The graph, the three-dimensional graph showed that they decrease going down. Now we notice hydrogen was really high, it was the Waldo, so it's not really part of this group. And there's another one, electronegativity. That's that word that kind of combines how well the nucleus is attracting electrons, really attracting electrons in a bond. And of course, if it doesn't take much energy to pull these electrons as you go down because it's getting bigger and electrons are farther away and feel the nucleus less, its attraction for its electrons or electrons in a bonds also decrease. These three factors, big atomic radius, low ionization energy, and low electronegativity, all define one thing, and that's a metal. Metals are essentially defined as having large atomic radii, low ionization energy, because they do what? They lose electrons. You can't find me a metal that becomes negatively charged. These charges in the upper right-hand corners tell us that they lose negatives. They oxidize. Metals oxidize. They lose electrons because of these three things. Now, before we talk about the what we call nonmetals, okay, which are the opposite, we'll describe them, we need to know where there's a barrier. And I'll explain. We notice that atoms get smaller going across and going up. So they become more non-metallic going to the left. Why? The Z number is increasing, the nuclear charge is increasing, so there's contraction in the orbitals. And as you go up, the N number, which indexes size, goes smaller. Remember, going down, what the biggest factor going down is that quantum number N increases, okay, extra shells of electrons. So the yin and yang in chemistry is about the fact that we have these metals who lose electrons and we have these nonmetals who gain. And now why? Well, their atomic radii are really small. And their ionization energy, the energy it takes to remove the electrons, if you remember the graph, was really high. The big bar graphs are over here. And their electronegativity, I'll put over here, okay, was also very high because they attract electrons in the bonds very well because their nuclear charge is so big, they pull their electrons in to be small. Because electrons are physically closer to the nucleus and attracted, it takes more energy to remove them, and therefore they attract them more. Okay, so these three, okay, values, when they go this way, represent nonmetals. They're the opposite of metals. So you can expect your nonmetals to be in the upper right-hand corner of the periodic table and your metals to be in the lower left-hand corner. But in truth, the most reactive nonmetals are up to the left, up to the right, sorry, and the most reactive metals are down to the left. That's the yin and yang, the ability to lose and gain. So, but there has to be some divider. And what's that divider? Well, on the periodic table, we have this staircase. And I'm just going to kind of write it in big, more bold lettering here. And this staircase kind of delineates the small atoms that are nonmetals from the big atoms, or the atoms that tend to gain electrons, which get reduced, from the atoms that what? Lose electrons and get oxidized. Remember, flow of electrons goes from the metals who gets oxidized to, generally speaking, nonmetals who get reduced. But what did I outline here? Well, these elements that live on the staircase, boron, silicon, arsenic, tellurium, okay, some people think astatine is also, and including antimony, Sb, and Ge, germanium. These elements here have properties of both. They're kind of in between. And we call these guys on the staircase semimetals, you'll hear, or you'll hear the word metalloids. And the bottom line is they have properties of both. Okay, So why do we care? Because the type of bonding that we're going to see is based upon what kind of elements are involved. Elements that lose electrons really well, and elements that tend to gain them really, have a high attraction. Low attraction become positive ions over here, and here become negative ions by gaining electrons. And if you look at the electron oxidation states, upper right hand corner, you'll see that most of these become negative. The top oxidation state is negative to show you that these elements have such a nuclear charge they gain electrons. So it's important to realize that, because the type of bonding really depends upon that. Now, so even though the most metallic elements, the biggest atoms, are over to the left and down, and the most non-metallic are up to the left, because we have this divider between nonmetals, which are in this region here, okay, and in truth, I'm going to, well, I wish I could, but this is the nonmetals here. It has to include the hydrogen, because if you remember our graphs, the hydrogen doesn't have a large radius. It has all the things that what? Nonmetals have, so hydrogen is a nonmetal. So generally speaking, okay, what we have is we have the, I'm just going to do this here. What we have is most of the periodic table, okay, which is under to the left, which includes all of this right here, okay, are your metals. Hydrogen is put over lithium because it has one valence electron, but it really belongs. Remember, it kind of sticks out. It's the different graphs that we saw for electronegativity, atomic radius. It has a small radius, a high electronegativity, and a high ionization energy. So it belongs, okay, it belongs to the nonmetals, okay, which means most of the periodic table are metals. And again, to define a metal, okay, is to see that it becomes positively charged. So all of these guys here are metals. All these guys become positive charge, right? So all of these below the staircase, including all of this area here, most of the periodic table are metals. All right, let's go on and explain some bonding. Okay, so we're going to start with the first type of bonding, which is ionic. Now, the AP doesn't spend a lot of time on this, but we have to know this, okay? So if you notice right here, we have here a metal. It's potassium, okay? It's an alkali metal. It's under sodium, okay? And if you notice, I wrote the configuration here. And 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And so this is the outermost electron. And so when we write something called a Lewis dot structure, we're trying to show how this bonds. So we're going to put one valence electron here equal 1 dot. Here I have 1s2, 2s2, 2p6, 3s2, 3p5. This is chlorine's electron configuration. And notice it has 5 plus 2, 7 outermost. So the dots on the out represent the valence, the outermost high energy electrons. These core electrons are not involved in bonding. They're too stable. Okay, so if you notice, potassium on your reference table is off to the left. It is, okay, an alkali metal. And chlorine is one of those atoms that are up and to the right. So this is a metal, and this is a nonmetal. So what's going to happen? Well, it's important to realize that the electronegativity difference, or the electronegativity of potassium, is really low. It doesn't attract electrons, right? It's the first proton with an electron in the 4th energy level. Chlorine is the 7th proton filling the 3rd, so it really attracts electrons. So what's going to happen here as I click? Well, the difference in electronegativity is going to be so great between them that what we're going to have is a transfer. And essentially, this electron moves over to the chlorine. And what happens to the chlorine? It becomes an ion. And to represent the fact that electrons were transferred, we write brackets. Very important. And I put the charges. Now, chlorine, we should recognize the fact that in chlorine, okay, it now became stable. Why did it become stable? Well, now by having one more electron, it fills its outermost. Now it's as stable, okay, as argon. Potassium lost its outermost, and now it's as stable as argon. So it's important to realize that. Okay, we call this potassium chloride to show that this is the name of the salt, and that's the chemical formula. And here we go with the transfer electrons when they become ions, and that's not what I wanted. Okay, so we're going to start with, okay, a metal. You notice that sodium, okay, atomic number 11, is on the left-hand side of the periodic table. It's clearly a metal. Big atom, holds on to electrons loosely. And then we're going to have chlorine, which is in the third energy level, but it's up to the right. It's a nonmetal. I'm going to put these together to show at the first type of bonding. So there's my nonmetal. It's got a small radius, high attraction for electrons, high electronegativity. Now, let's understand that in bonding, to do Lewis dot structures, what we want to show is dots, the valence dots, or the valence electrons. So for sodium, 3s1 is the valence electron. And for atomic number 17, 17 electrons, the valence electrons, the outermost high energy electrons, is 7. So what we do is we draw dots, and I'm going to put one dot here to show that sodium has 1 valence electron. And then I'm going to do red dots, and chlorine has 7. So I'm just going to put these together, and some people think the top dots are the 3s2, and people put dots here like 1, 2. These are the p sides. Some people do that. Okay, it's 3p5, so they pair up. There's 2 pairs and there's 1 left. Bottom line is, it doesn't really matter. There's 7 dots. Okay, as ugly as they might be. Okay, now what do we know? Well, we know that sodium, being a metal, has a very low electronegativity. It's about 0.9, very low. It doesn't attract electrons very well because it's a big atom. Electrons are held loosely. It doesn't have enough Z number to attract them. Chlorine, being a nonmetal, has an extremely high. Okay, it's 3.2. Okay, it's very high electronegativity. So the difference in the what we'd say the pulling strength or attraction for electrons in a bonds is so much bigger for chlorine. What chlorine's going to do, it's going to pull that electron away. And as we've learned in redox, sodium's going to what? It's going to get oxidized. It's going to lose that electron. And chlorine's going to get reduced as it gains electron. And the process here, we show this, I'm going to get rid of the, we show this, okay, by showing that this electron from sodium, okay, now moves to the chlorine. There's a complete transfer. Now, when we have a complete transfer, because metals always have a low attraction and nonmetals always have a high, that combination always is going to lead to oxidation and reduction. But what we do to show that electrons are transferred, we write brackets. This bracket here shows us all these electrons belong to chlorine, and because it gained an electron, it is now -1. We also know that the ionic radius is bigger now. A gained electron got bigger, okay, because the effective nuclear charge electron cloud is lower. Now, sodium has no valence left. It's empty, and because it lost its outermost, and now it's +1. And so the Lewis dot diagram, I'm going to rewrite this, is Na with no valence electrons left, and it's +1. Chlorine is going to started with 7 of these, now has 8. It gained 1. It took the electron from sodium, and now we draw brackets to show that this thing is now -1. We're going to have no sharing here. Now, interesting enough, you should notice that by the transfer of electron in this type of bonding, what we did is sodium lost its outer electron. And looky here, now it's got a complete filled second shell. Okay? And chlorine, by gaining an electron, also attains a noble gas configuration. So this becomes now a 6. So they both get stable as their noble gas counterparts. Sodium becomes as stable as neon. This is the same. Sodium plus has the same configuration as neon. It doesn't become neon because the proton number doesn't change, but we know it becomes as stable. And this chlorine, by gaining 1, becomes as stable as argon. It doesn't become argon, but it achieves a stability by filling its energy level. How do we know it's stable? Well, this is sodium chloride. We write NaCl. Now, we write solid because the attractive force between a positive ion and a negative ion is very strong. So strong, okay, that these things have extremely high melting points. Okay? Now, it's important to notice that ionic compounds, and this is an ionic bond because you just made ions. So the type of bonding between a metal or a nonmetal where there's a transfer is an ionic bond. Okay? And these ions, like sodium, are +1 in all direction, which means they can what? They can attract a negative in all direction. Remember, the chlorine is going to be bigger. And this chlorine is negative in all direction. It can attract the sodium in all direction. And what you're going to get is a crystal lattice of ions. And I showed this in the class all year long. This is an ionic compound. It makes a crystal lattice of ions that keep going in all direction. And when we write a chemical formula for ionic compounds, we always write the lowest ratio. It's important to understand that ionic compounds make crystals of ions. That dominates their properties, makes them very stable, hard to separate, and therefore their melting points are extremely high. Okay, so how do I know I have ionic? Well, if I have one of the big atoms that are what? Below the staircase, most of the periodic table are metals, and they're going to hook up with a non-metal. There's going to be a transfer. Electrons are transferred from the metals to the non-metals, and you're going to make ions. Okay, and we have a naming system that we did over the summer, and we always put the metal in front. The metal is sodium, and if it's a binary compound, we put the ending name. So this is sodium, and it ends with chlorine, but because it's binary, it ends in IDE. We've been through that. Okay, so let's go to our worksheet, covalent worksheet for a second. The back side of the ionic worksheet, and if you notice, I have magnesium with fluorine. Okay, how do I do this? Well, I'm going to start with magnesium. I go to the periodic table, and then that magnesium loves become +2. Okay, and then I know fluorine from the periodic table loves become -1. And I know that because I can look at the upper right-hand corner, or I can look at the electron configurations and see that magnesium's got 2 valence that are lost, and fluorine has 7 valence, means it wants to become -1. And a really quick way to write these is a crisscross method. This -1 is going to go down here. This +2 comes here. And you can think with me for a second. I'm going to put as many positive 2's, okay, next to each other, and to enough -1 ions in order for this entire compound to be electrically neutral. So if you want to think with me, Mg starts with 2 valence electrons. If you want to write this, fluorine has 7. I'm just going to do this once because it's pretty simple. From electron configurations, well, what's going to happen? Well, because this is a metal with low attraction and fluorine's a nonmetal with high, there's going to be an attraction. There's going to be a what? An absolute transfer of electrons. So fluorine's going to get its 8, become -1. Magnesium cannot become +1, so it needs to lose another one. So party people, okay, what's happened to magnesium? What's it going to do? It needs to lose 2, so it needs another fluorine. Okay, so what's it going to look like? I need an Mg who lost 2, is empty and +2. It lost its valence. I need a fluorine who starts out with 7 dots, 7 valence electrons, is going to gain 1 from a fluorine to become -1. And you're going to need another fluorine. You say, where did that come from? Well, there's a bunch of them around. And this fluorine starts out with what? 7, and it gains another 1. So the big dots that I drew represent the electrons that came from the magnesium. And this represents the Lewis dot structure for magnesium. The chemical formula, hey, it's Mg, who's +2, needs what? 2 fluorines who are -1 individually for the whole thing to be 0. The chemical name is magnesium, name of the metal, and the ending is fluoride, IDE. And that's really what you do here. Okay, if you're going to do the crisscross method, there'd be 2 what? Fluorines to 1 magnesium. The bottom line is you need as many ions to make this stable. Remember, this is a lie. MgF2 is basically a solid because of very strong attractions. This is a crystal, and this is the lowest ratio in a crystal. Continue with this and look at the key. Let's go on to covalent bonds. Now in covalent bonds, and these are the bonds that we're going to spend most of the time, it's covalenting, meaning we're going to use each other's electrons. So what's covalent bonds? Well, we're going to have a nonmetal like hydrogen who has a high electronegativity, and then we're going to have another nonmetal like chlorine that we just picked. These guys can bond, but they do differently. Notice there's no metal here, which means the electronegativity of chlorine is about 3.2. The electronegativity of hydrogen is about 2.2. These are both high. Now, chlorine's a little higher, so what's going to happen is it's going to pull electrons a little closer. But let's draw in the valence electrons for hydrogen. It's just 1s2. Oh, I'm sorry, 1s1, so 1 valence electron. Now, chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. It has how many valence electrons? As we talked about, 7. So we draw 7 dots. 1, 2, 3, 4, 5, 6, and 7. And party people, okay, what do we have here? Okay, well, I should really draw this pair closer, but sorry, what we have is nobody's strong enough. And I'm going to erase this a little bit. Okay, the electron from the hydrogen is going to be here, and the electron from the chlorine is here. And because they're both have high electronegativity, attraction for electrons, they're both pulling on this electron. So hydrogen is pulling on these two, and chlorine is pulling on these two. Because they're both pretty high and they're both nonmetals, nobody is strong enough to rip the electrons away. So they're forced to share. In the other example, ionic bonds, there was what? A transfer, because the difference in electronegativity was huge. And there was a transfer that made ions, and they stuck together because of ions. That's why it's called ionic bonding. Here, because there's no metal, we don't have that. We're forced to share. So hydrogen, by sharing, feels like it's 1s2 and as stable as helium. And by sharing, this one feels like it has 8. And so we write covalent bonds with dashes, H dash with chlorine, and then we put in the valence electrons. Now, real quickly, the bond between the two nonmetals, okay, is considered polar or nonpolar. Polar means you have differences. Well, this is a polar bond, and the reason why it's a polar bond is because they're sharing unequally. Why are they sharing unequally? Because they have what? They have two different electronegativities. This chlorine pulls this a little closer. So if you talk about the distance in a bond, these electrons are closer to the chlorine side. If I rewrite this, this is the area of the bond. This pair of electrons are closer to the chlorine because it's a little stronger. 3.2 is pulling on these more than the what? 2.2 can pull away. So this is unequal sharing. And so that this side of the bond has a pole. It's a little more negative than this side that kind of lost them. Okay, so unequal sharing creates a polar bond. Now, if I draw hydrochloric acid, I draw it something like this. There's my H, and there's my bond to a chlorine. Well, where's the electron-rich side of the molecule? Right here. We'd call this a partial negative side, and this is the partial positive side. Now you say, whoa, what's partial mean? This is partial signs. Because there wasn't a transfer, okay, we can't say this side is -1. So we say it's partially -1 because of the unequal sharing. But if you can see here, there's a lot more electron density near the chlorine side. So we call this a polar molecule. And one way to notice about polar molecule is there's going to be asymmetrical distribution of electrons. What's an example of a nonpolar molecule? Okay, well, nonpolar molecule would be when you have something like carbon, who has 4 valence electrons. We'll do electron dot diagram of methane, CH4. Notice carbon is a nonmetal, so is this. Hydrogen, we'll write by writing blue, okay, brings 1 valence electron because it's just 1s1. Carbon, if you remember, is 1s2, 2s2, 2p2, has 4 valence. I put 4 dots out. H has 1 dot. And what we have, party people, is that by sharing, each hydrogen feels like it has 2. Each one thinks it's 1s2. And by sharing for the carbon, okay, it had 4 valence, and now it has what? It feels like it has 8. But where are the bonds? Well, the bonds in between the carbon and hydrogen are polar because they're 2 different atoms, okay, that have 2 different electronegativities. Carbon actually is a little more electronegative, so this should be pulled closer, but you don't have to draw that. So anytime you get a polar bond, it's 2 different, what? 2 different nonmetals. So we have 4 polar bonds. Now you say, Mr. Grodsky, I'm sharing unequally. So is the molecule polar? The answer is no. Because of the symmetry of the molecule, this side is the same as this side. Ooh, Christmas. Okay. This side is the same as this side, the same as this side. Because of the symmetry of the molecule, okay, there's no side that has more electrons than another. The way that I like to think about it is that because there's unequal sharing in 4 polar bonds, And because those polar bonds are the same all the way around, we like to say there is what? Equalness on every side of the unequalness. The unequalness due to the of the unsharing of electrons, or unequal sharing, is the same on all sides. So it's equal on all sides in its equalness. Bottom line, it's the same all the way around. We'll start with that. That means it's a nonpolar molecule, but it does have polar bonds. Okay, and that's how we're going to start this. Okay, and if you talk about oxygen, oxygen has 6 valence electrons, so 1, 2, 3, 4, 5, and 6. Okay, another oxygen molecule will start with a bond 1, 2, 3, 4, 5, and 6. When we check out the Lewis dot diagram, we always start with one bond. You can see that this oxygen by sharing has 1, 2, 3, 4, 5, 6, 7. And this oxygen by sharing has 7. 1, 2, 3, 4, 5, 6, 7. So party people, that's not going to work. So you say, well, what do I do in this scenario? You need another bond. So move this one over, okay, and you make another bond. A bond is a pair of electrons. Okay, I don't know what color I had, but I'm going to move that one here to here and this one over to here. And so what it gives me is that now by sharing 1, 2, 3, 4, 5, 6 with this 1, 2, 3, 4, 5, 6, this oxygen by sharing feels like it has 8. And we needed a double bond there. So O has a double bond with another O. Don't forget lone pairs. Okay. And those are the basics here. And these are called covalent compounds. And by the way, these covalent compounds don't have high melting points because they make molecules. This molecule will attract another molecule by intermolecular attractions. This could be an H, that's what, partial positive, and this is a Cl. And these attractive forces are always going to be weaker than bonds. So these guys stick together by weaker forces of attraction. Molecules, okay, little particles are not in a crystal format, so they're not as stable, so the melting points are lower. Think of butter, plastics, okay? They melt at low temperatures. Think of ionic compounds as rocks on a beach. They require a lot more energy because they're in crystal patterns. Okay, so those are the basics of the two types of bonding. Ionic, which form crystals of ions, which are very stable and hard to separate, and then the sharing of electrons between non-metals. Metal, non-metal, has a transfer. Non-metal is forced to share. Okay, all right, that's what we needed to do to start the rest of the homework.